Now that we have a basic understanding of what's actually happening during model training, let's train our model. I created a simple Python script that we can use to train our model, visualize the accuracy of the training, and iterate over adjusting our hyperparameters to improve the model's accuracy or minimize the error. To simplify things, I've also created a wrapper module that abstracts away the TensorFlow, Keras, and plotting details so that we can focus solely on training itself. The prompt user function allows the user to adjust the hyperparameters on each training iteration. We'll start off with some hard-coded values for our hyperparameters. Keep in mind that the learning rate controls the step size during optimization. Batch size determines the number of data points used in each update, and epoch represents a complete pass through the entire training dataset. Our model is trying to predict fare, the label, by analyzing the relationship between fare and trip miles, the feature. Recall that the last block of code in our Explore Data Python script split our original data set into training data and validation data. This is important because we need to ensure that we have data that the model isn't trained on that we can use in the validation step of our ML pipeline. Since we're in the training step, we read in our training data. Now on to the more interesting logic. In the context of a while loop, we instantiate a model object from our wrapper module, passing in our training data, our features, columns used to make predictions, and our label, column containing the value we are trying to predict. Next, we adjust our hyperparameters, train the model, and graph our results. After graphing the results, we ask the user if they want to save the model and exit. This gives them an opportunity to analyze the graphs and decide if they would like to retrain the model with different hyperparameters to try and improve its accuracy. Once the user is happy with the results of the training, they respond yes to the prompt, and the code falls out of the while loop and the model is saved. Saving a trained model writes the configuration, weights, optimizer, and metrics into the file system. You can load a saved model to perform validation and to productionalize the model, or serve the model. And we'll do both of those in just a few moments. Now let's run our script and train our model. For our first iteration, we'll just use the hard-coded hyperparameters and see where that gets us. The training iterates through 20 epochs, printing out the root mean squared error for each epoch. It also prints out the equation of the prediction line. It's hard to tell just by looking at the data printed to the console if our training has resulted in an accurate model. So let's take a look at our graphs. On the right-hand side, we have our model plot. Fare, the value we're trying to predict, is on the y-axis, and trip miles, the value that we're using to make our predictions, is on the x-axis. The blue points represent a few data points from our training data, and the red line is our candidate prediction line. On the left-hand side, we have our loss curve. The y-axis represents the model's error. In our case, since we're using a root mean squared loss function, it's the square root of the average squared distance between the predicted and actual fare values. The x-axis represents the training epoch hyperparameter, and the red line is the loss curve itself. To assess the accuracy of our training, we start by looking at the prediction line of our model plot to see how well it fits the sample training data, the blue data points. While the prediction line looks close to a good fit, it's clearly skewed a bit. Next, we take a look at our loss curve. Instead of a smooth, consistent decrease in error, the error is wildly oscillating back and forth, resulting in a jagged loss curve. If we compare the shape of our loss curve to the desired shape, clearly something is off. A jagged loss curve is an indication that our model is not converging, or that it is not learning in any consistent or meaningful way. Choosing a learning rate that is too large may be the cause, so let's iterate on our training and reduce the learning rate. Let's try a learning rate of 0.1 while keeping the other hyperparameters the same and see how that impacts our model plot and loss curve. Looking at the model plot, our prediction line still looks a bit skewed, this time in the other direction. Our loss curve is no longer jagged, but it's still not the optimal shape, so let's iterate on training again. This time, let's try a learning rate of 0.001. Now the prediction line of our model plot looks like a pretty good fit to the plotted training data, and the shape of our loss curve looks to be good as well. In this video, we walked through a simple Python script to train our model and iterated through a few training runs to improve the accuracy of our model. All that's left is to save our trained model so that we can use it in the validation step of our ML pipeline. Next up, model validation.